Good morning. Welcome back to the Utah Connected webinar series. This is the fifth of 6 webinars in the series hosted by the Utah Department of Transportation. My name is Muriel, and I will be your facilitator for this event. The webinar series, Utah Connected webinar, is intended to foster collaboration and promote information sharing among UDOT and its partners across the country. It highlights 6 successful deployments across Utah, including significant deployments with connected vehicle technology that has helped to improve mobility, safety, and quality of life right here in Utah. Collectively, we have seen over 1,000 individuals participate in our webinars so far. These webinars are free and open to the public, but advanced registration is required. All meetings are being recorded, and the recording will be made available to the public within 1 week of each webinar. On the UDOT website, we will provide a URL for that as we go. We would like to note that while you'll see showcased here certain technologies, UDOT does not necessarily endorse any one company or product, but has had great success in working with its partners on these deployments. Before we get started, we wanted to hear from all of you to see who's been joining us this morning. So we wanted to pull up a poll and ask you just a few questions. First of all, what role best describes you? Are you an engineer, a planner, a researcher, a consultant, policymaker, or something else? Secondly, what industry sector do you work in? The public sector, the private sector, maybe for a nonprofit or an academic institution or something else. How long have you worked in the field? Less than 5 years, 6 to 10 years, 11 to 15 years, 16 to 20 years, or more than 26 years? We'll give you just a minute to take that poll. We'll go ahead and end the poll now. Looks like we have a lot of engineers joining us today. You'll appreciate the acronyms. But we also have planners, researchers, consultants, and one policymaker with a representative sampling of folks across the industry. We also have 14 folks who may be representing another type. In terms of industry sector, we have a good mix of public and private, with some nonprofit and academia represented as well. And across the board, folks that have just started out in the profession and folks that have been here for quite a long time and everything in between. So thank you so much for participating in that poll with us. We'll now get right into it. So with over 3,200 miles of fiber, UDOT has one of the most robust DOT-owned fiber optic networks in the nation. Distributed Acoustic Sensing, or DAS, which is fiber sensing, uses fiber optic cables buried along the road to monitor roadways in real time by detecting acoustic events in the vicinity of the fiber. Those could include crashes, avalanches, vehicle speeds, and travel times.
In a minute, so it's good to have you back.
This information can then be efficiently transmitted to UDOT's Traffic Operations Center, where it can be used to assess traffic conditions, dispatch response vehicles, or even warn motorists of hazardous conditions. This UDOT fiber sensing project is one of the first in the entire country. It aims to provide critical safety and maintenance information. The webinar will provide an update on the project's progress and highlight its next steps. I would just note, if you have any questions throughout today's program, please feel free to submit them in the Q&A. An icon for that is located at the bottom of your screen. If we are unable to answer all of the questions today, we will follow up with you via email directly after the webinar. We've got quite the lineup of subject matter experts who have been kind of managing this day to day for the past several years. We'll first start with Blaine Leonard. For those of you who have not gotten the pleasure of meeting Blaine, he is the Transportation Technology Manager at UDOT. In this role, he leads the planning and deployment of connected automated vehicles. He has chaired the American Association of State Highway and Transportation Officials Connected Automated Vehicle Working Group and has led the SPAT Challenge Tactical Working Group. He is currently co-chair of the AASHTO Technology Subcommittee. Prior to joining UDOT in 2001, Blaine spent 20 years in the consulting engineering business. Blaine has a Bachelor and Master of Science in Civil Engineering from the University of Utah. Blaine.
Thank you, Muriel. I appreciate that introduction, and I'm happy to have everyone with us today. Let me pull up my presentation. It's really hard for me to believe that we are now in the 5th of our 6 webinars. We have been planning this webinar series since the very beginning of 2023, and a lot of work has gone into them, and all of a sudden we're at webinar number 5. The first 3 webinars, or the previous 3 webinars, were very much focused on our connected vehicle deployments. That's where a lot of our ATC-MTD effort has gone and a lot of what our program does. Today is a shift for us. We're moving to another technology where we use fiber for situational awareness. But before we get to the topic, I want to offer some thanks. First of all, to the Federal Highway Administration, their ATC-MTD grants team, and their local office, who have worked with us throughout this ATC-MTD grant program over the last several years. It's their funding that brings you this webinar series and most of the work we talk about in this series. If you're interested in more information about the ATC-MTD program and our particular Utah Connected grant, that was in webinar number 1. And the recording and the presentations are posted at transportationtechnology.utah.gov, our website. I want to thank Muriel and her team at X Factor, who have done all the heavy lifting and work to coordinate and organize and sort of beat us all into shape so we could pull these webinars off. We appreciate them. And we're grateful for today's presenters from UDOT, from Duraline, Luna OptiSense, and WCG. I will note that the speakers today, Andy and Alistair from Luna OptiSense, are coming to us from England. It's very late in the evening there, and so we really appreciate them taking some of their evening time to be with us. Of course, we want to thank all of you who are joining us today live, those of you who will watch us later and have participated in any of our webinars. We've had over 500 people sign up for this series of webinars. We have 150 or so of you right this moment logged on with us, and we appreciate all of you being here. This series of webinars, there are 6 of them, is really intended to share information that we've learned through our work that's been funded by this ATC-MTD program. We want to give away as much as we can and let everybody else learn from our mistakes and our lessons and our deployments. We want to foster collaboration, and we want to encourage all of you to deploy similar technologies based on some of the things that we've done to help advance these technologies so that we can all meet our agency goals. At UDOT, our primary goals are focused around safety, zero crashes, injuries, and fatalities, and mobility. And the things that we do in our Transportation Technology Group primarily focus there. Safety is our number 1 strategy. Much of what we've done in the short term focuses on mobility. As sub-goals, we're trying statewide to achieve situational awareness, understanding what's going on in our network, and to prepare for production vehicles which come with V2X equipment on board so that we can achieve safety. Today's webinar will focus primarily on this concept of situational awareness, helping us to understand what's happening along our roadways with all of our travelers. So that's what gets us to the Distributed Acoustic Sensing program to achieve situational awareness. And that's the focus of today's webinars. When we began to consider distributed acoustic sensing, we wanted to figure out what we could do to augment or potentially replace some of the sensors we have along our roadways. Distributed acoustic sensing is a concept that uses fiber that's laid along the road. As you know, fiber is transmitting data over a light stream, and any vibration in the ground picks up, it disrupts the light stream, and we can identify those disruptions very specifically as to location. So we wanted to evaluate the capabilities of distributed acoustic sensing and these disruptions to monitor traffic speed, travel times, queue and congestion conditions, because those cause ground vibrations that can be picked up. We also wanted to see whether we could detect incidents and crashes and rockfall and avalanche events. I'll describe in a minute that we've deployed this in along some canyon roads where rockfall and avalanches are fairly frequent occurrences. We also wanted to assess the user interface of these systems. How easy is it for us to see and get the information? And then assess the feasibility and deployability and operations of these systems. If you've been on any of our other webinars, you've seen this map. It's the Wasatch Front of northern Utah, the flank of the Wasatch Mountains, which really forms the greater Salt Lake metro area. And I've used this map to show our connected vehicle deployments. In this particular instance, here in northern Utah, I've put a blue box around Big and Little Cottonwood Canyons. These are two canyon roads that go up to 4 of our 8 or 9 premier ski resorts. They're heavily traveled roads with a lot of interest both winter and summer, and a lot of activity in the canyon. And so we chose these specifically as places where, although we have cameras and radar and other sensors in the canyon, the narrow, windy road geometry makes it so we can't always see what's going on in the canyon. Here's a zoom in of those two canyons. This comes from our fiber map, and the colors on the road really represent fiber type or number of strands, those kinds of things. So this is really a definition of our fiber location. I show Big Cottonwood Canyon, which is about 14 miles long, and Little Cottonwood Canyon, which is about 12 miles long. And the fiber placement and the DAS program covers both of these canyons, as well as Wasatch Boulevard at the left side of the image, which connects the canyons. The equipment is located in a fiber hub building inside the little blue box on the left side of the image, which is at the intersection, the interchange of our Interstate 215 that circles the valley. You'll see more images of the canyon. You'll see more maps of the canyon. I just wanted to start you out with an understanding of the geographical context for the project. As I mentioned, fiber in this case senses ground vibrations and uses those vibrations to be able to detect traffic movements from which we can derive speeds and travel times and sense impact events. And the speakers today will talk a lot about very specific issues, show you specific examples of those kinds of events, how they measure them, and how we use them. Here is just one quick high-level example. You can see at the top of the screen what we call the waterfall, and the experts will sort of describe to you what that is and what you're seeing. You'll notice that one zone which looks different than the rest, and below it you'll see the type of fiber happens to change in that particular location. So one of the primary things we learned, and again, others will talk about this, is that fiber placement, fiber type, fiber backfill is very critical to the operation of the DAS system. And this simple graphic sort of gives you an example of that. From a programmatic standpoint, our next steps, and I'm sort of jumping to the end for me, but you're going to hear a lot of detail in between. We're still tweaking the algorithms to make sure that we fully understand what the fiber is seeing in the canyon and how we can make use of that. We're refining the notification process so that emails can be directed, alerts can be directed to appropriate people at appropriate times, containing useful information and reducing false positives. We don't currently have specific plans to expand this system because we're still evaluating some of those things. We do have a cost model that allows us to compare this in a general sense with other kinds of technologies like cameras and radar sensors and things. We don't believe that this will replace those. You can't see something like you can with a camera, but we believe it can augment those. As we look at cost effectiveness, it would probably be most effective in areas where there are other technologies maybe aren't as frequently placed, specifically in corridors that might be more rural. And that was really our original intent, and one of the reasons we picked canyon roads, because we could augment the limited view we have in those areas. So we're still evaluating some of those things and figuring out what we could do with this. This was an incredibly valuable experience working with Dura-Line and Luna OptiSense to understand what this technology could do. It's a relatively new technology. We first identified it a number of years ago and saw that it was being used in North Dakota for transportation uses, in New Zealand for transportation uses, but not a lot of other places at the time. And that's what piqued our interest. And we're still sort of evaluating what we could do with it. So with that introduction, I will turn it back to Muriel, and we'll move into some of the experts who can give us a lot more detail about this system and our deployment of it in Utah. Thank you.
Fantastic, Blaine. Thank you so much. It's nice to have that context. Now we're going to do a deeper dive with Paul Dickinson. Dr. Paul Dickinson is the Director of Business Development at Dura-Line and Chairman of the Board at the Fiber Optic Sensing Association. That is a telecom industry veteran. He has over 32 years of experience. Paul began his career as an AT&T Bell Labs materials research scientist, developing new optical fiber cable material formulations before moving on to a wide variety of technical, marketing, and sales management positions within Lucent Technologies, OFS, and now Dura-Line. Paul is currently involved in innovative business ventures, including strategic planning and development of fiber optic sensing solutions in a wide variety of vertical markets. Paul earned his bachelor degree in chemistry from Cornell University and a PhD in polymer science from the University of Connecticut's Institute of Material Science. I have to say he's the first person I've ever met with a PhD in polymer science. So with that, Paul, we'll kick it to you.
So Muriel, I watched The Graduate one too many times, I think. If you remember that scene where Dustin Hoffman was coached by his uncle to get into plastics. So that's my story there. Let me start by sharing my screen. Is my screen visible?
Yes, it looks great, okay. Paul.
Fantastic. I'm not a Zoom guy. I'm a MS Teams guy. So Blaine did a fantastic introduction, which was absolutely wonderful. And I am going to now continue the enviable position, at least for me, of setting the stage before we really dive deep into the technology. Speaking for myself at Dura-Line, I'm very excited to share the virtual stage with Blaine and the entire UDOT visionary team. It's become apparent to us in our collaboration just how future thinking Blaine and UDOT is, and how wonderful it is that they're willing to share their ideas for the benefit of everyone in not only DOT end users, but the ecosystem of ITS. So I certainly did not understand it all, but I thoroughly enjoyed the other 4 UDOT connected webinars. As Blaine said, we're turning the corner here, and we're getting into technology that has been years in the making, but is really emerging in a wonderful way for highway transportation. So our reliance on technology and the ability to benefit from technology is reaching new heights every day. Fiber connectivity is no longer just a convenience, it's a necessity that's becoming ubiquitous. So I went ahead and I boldly put the phrase "seizing the moment" on this slide, since I firmly believe that funding and technology stars are aligning in a rather unique way for end users, designers, and partners to look at how to leverage this technology for complementing the surge in broadband that's occurring and will continue to occur for the foreseeable future. So across the globe and in the US, new funding from public and private sectors is available that's going to meet this rising demand and appetite for innovation. And all of this complements and gives us new abilities to leverage our fiber infrastructure. So it's my view that organizations should seize the moment, so to speak, as I put here, to take advantage of this unique opportunity in time for near-term and longer-term opportunities. I will now move to the next slide. So just a quick introduction for my company, Dura-Line. Dura-Line is a leading global manufacturer and innovator, has been for over 50 years, continues to transform infrastructure that's we require for communication. And I know many of you both embrace and push back on technology. I know I certainly do. Classic example is kids or maybe our spouses or ourselves in front of our screens all day, but it's unavoidable. Technology, data, and constant communication are more intertwined with daily lives than ever before in human history. And Dura-Line provides that essential infrastructure, traditional conduit, novel new conduits like Future Path and accessories to make this possible. So today, hopefully, we're going to illustrate for you how to further the benefits of what's already in place, this product set that's in our ground now or aerially, and it's going to become even more prevalent going forward for the use of the intelligence that this can provide above and beyond just datacom and broadcom. So just to close on Dura-Line, we focus on innovative product solutions through customer insight, and we do indeed create the pathways that the fiber cable uses to connect all of us, serving wide variety of markets, including telecommunications, enterprise, energy, and now transportation. One more slide on conduit, and I promise conduits will go away for the remainder of this presentation, but it's important in setting the stage for how this all interconnects. So this is what a conduit looks like, for those of you who may never have seen it, with fiber cable inside. The UDOT technology we're presenting today and talking about is not about conduit at all per se, but it's about the novel multi-use applications that can result for the use of either the existing conduit that's in place today or the conduit that's going to go in going forward. So it's important for this audience, I believe, to understand the interrelationship between fiber. Blaine already mentioned a few minutes ago that the fiber selection is important. The interrelationship between conduit, fiber, and what we're about to talk about. So in order to place that fiber, for those of you who aren't familiar with underground infrastructure for future growth, you need a conduit system. You need something that's robust, reliable, scalable, upgradable. So this shouldn't be new to all the engineers on this call. What's new is that the technology we're talking about comes from the same optical fibers in the conduit that were put in for an entirely different purpose, communication. So we're leveraging those for a new and exciting application. So just one last depiction of what you're looking at here. What you see here are various conduit designs, both a traditional single pathway on the right and the more modern multi-pathway conduit systems that take advantage of high fiber density and what are called microcables. So these higher density cables combined with multi-path conduit enable end users to have this scalable system that can continue to put in bandwidth over time without incurring labor costs and digging up the ground time and time again. This speaks to what probably others on this call are familiar with, called dig once, where you want to spend all the time and labor digging up the ground once and then have a system where you can incrementally add to it over time. So as designers, engineers, and end users consider how to implement what we're going to talk about today, you got to integrate, and that's the point of this slide. You got to integrate your conduit placement, your selection, your fiber cable selection, so it all works together as a total solution. Now, this is a little bit of an eye chart, so I'm not going to spend too much time on this, but the point I want to leave you with today, the takeaway, is I want you to realize that conduit and fiber are everywhere, and it's only going to continue to become more prevalent. This includes everything from long-haul undersea transmission between continents to long-haul cable across the US, to middle mile routes that eventually branch off to enterprise and fiber to the home. So for the purpose of this presentation and audience, an ever increasing amount of conduit and fiber cable is being put in our right-of-ways along the highways and the roadways in the US. So that's how this ties into what we undertook with UDOT a couple of years ago to really dive into an understanding of how we could leverage this. The main point of this slide that I want to leave you with is there currently exists and there will be a growing need to leverage this infrastructure for more than just the data communications that already are in place, and to gather more insights from the fiber to the extent that we can. So I want to tell you how this technology works a little bit before we start diving into specifically the transportation aspects of this. Blaine already touched upon this. So if you look at the photograph of the box that says interrogator unit, that's essentially a rack-mounted piece of electronics equipment. And the purpose of that box is to inject pulses of laser energy into an optical fiber and then detect what's called backscatter from that fiber. So it basically sends light out and light comes right back to the same box. And that's what enables us to turn an entire cable into a very long, continuous, or distributed sensor. So if you have, for example, a typical communications cable running in parallel to an asset, that asset could be a pipeline, a railroad, or a border, or of course, for this webinar, we're focusing on roadside. What you do is you basically turn that entire length of cable into a sensor with repeated sensing positions. So the resolution can vary depending on the application and the data set, but a good rule of thumb is to think of the resolution of about 10 to 20 feet over, say, a distance as long as 25 to 60 miles. So also, if your monitored assets longer than the reach that I just described, you simply have to put another interrogator box in line and concatenate them. So in the case of roadside, this simply means having an interrogator equipment in a DOT hut spaced out at appropriate intervals. The other thing is, don't think of the fiber as needing to complete a loop or a circuit. That's often a question. You simply send out signals in the same fiber and it comes back on the same fiber in the opposite direction. The other important point is electricity is not required on the cable itself. It's just required to power the box on one end. So what does that do? It leaves the interrogator or the hut as the only power mechanism, and all the rest of it is an extremely passive underground system that benefits from the similar decades-long longevity that a buried telecommunication cable has in conduit. So the other thing you need to know is, depending on the configuration of the equipment used, we can detect changes in temperature with this technology. We can also detect changes in strain or compression. As Blaine said, that the fiber is essentially feeling what's going on in the environment. But in many cases, what's most important, and the technology we're talking about here for UDOT, is that we can detect vibration. And that's what's called distributed acoustic sensing, or DAS for short. So with this technology, we can hear and classify and locate activities such as shown here in the black silhouettes. We can actually hear and classify digging, excavation, tampering, and also vehicles, of course, which are important to what we're also talking about here. So through the rest of this presentation, you're going to see a lot of under the hood analysis, or so to speak, how the sausage gets made, with a lot of data-rich screens. But don't let that scare you. The important thing to remember is that the application for the end user or the operator, or in this case, the DOT Engineering Center, is typically to receive integrated information into their existing monitoring system in the case of traffic monitoring, and also to provide live preventative alerts in the case of live damage prevention. And the final point I'll make on this slide is simply that the technology is very well established with use cases in many vertical markets. In fact, it was mentioned in my bio, I chair the Fiber Optic Sensing Association. This is a nonprofit organization, and this technology has been out for decades in other markets. So we constantly share information how to best to integrate this with enabling systems such as we're talking today, highway transportation and ITS systems. So before I pass the baton to Luna and UDOT and Michael and Chuck to describe the technology and the results from this wonderfully collaborative work we've done with Blaine and his team, I want to provide just a little bit more context for all the engineering companies, designers, funders, and end users in this audience today. So I'm going to assert something. I'll pose the following question. Might there be a beneficial perfect storm situation that's brewing right now for underground infrastructure and specifically for DOTs in the US? I'd like to suggest that's indeed the case. And I'm going to give you 6 reasons I believe that's the case. First of all, let's start with the most obvious. US and the world see optical fiber as the preferred datacom medium. Whether it's long haul routes, direct to the home, or critical backhaul for 5G wireless, optical fiber is the de facto technology moving forward for high-speed symmetrical data communication. Secondly, there's a tremendous ongoing demand for Broadcom services to reduce the digital divide. I remember data from 2020 that said the US was 27th in the world with respect to global internet connectivity. And, that's appalling. So things have improved, but it's still accepted that the US is behind. And that, of course, what's driving this nationwide focus and funding to serve both the city and particular rural citizens with providing them adequate symmetrical broadband. Based on that, the government and the private sector funding for optical infrastructure is currently at an unprecedented level through infrastructure bills. And this is going to go on for a long time. More than $90 billion has been or will be allocated to the US broadband-related projects in 2018 to 2028. You know these terms as BEAD or middle mile funding, but there's also an increasing amount of funding that's not automatically allocated state by state. And it requires competitive proposals which benefit from differentiation. And one example of this is this year's DOT SMART grant funding, which I've learned about recently. This program, I think, actually has a deadline in October. And I think it's an annual program where they provide funding every year for innovative projects. And then number 4 is there's a growing emphasis on sustainability and the need for resilience. And this crosses outside of highway transportation and ITS systems. Just to give you, again, more context, outside of the highway system, our nation's infrastructure in general is coming under scrutiny with respect to robustness and the ability to handle future demand. You've seen things on outages, a lot of talk about cybersecurity, third-party intrusion, and minimizing life safety events. I've read a lot in the press, and it's being discussed throughout Congress now about power substation attacks, utility outages, ransom events. It goes on and on. Folks are searching for a way to stop bad things from happening. And then there's also a desire to make the money go farther. So how do we lower the total cost of ownership by looking hard at both OpEx and CapEx? Blaine already mentioned, we're now, as the next step of this project, looking at how to integrate this in the portfolio along with other technologies available. So, for example, reducing damage and cuts and the time to locate them when they happen, that's going to have significant direct and indirect costs. So now coming full circle to roadside, which is the topic today, there's an ever-increasing importance of ITS. The last Utah Connected webinars emphasized where we're headed with this technology, and it's pretty exciting. There's a recognition that roadside fiber is critical or beneficial, if not critical, as a complementary precursor to both 5G backhaul and connected vehicle technology. So what does this do? This technology, with all this said, it means that technologies can leverage this new build roadside fiber that was originally unintended for this purpose. So if we can leverage that for other purposes that will provide the ability to differentiate grants and proposals, and will provide the ability for the government to see that their money is being well spent, it means that technologies can leverage this in ways that we didn't anticipate a decade ago. And when all the dirt settles, and that was a pun intended, so to speak, how do you improve the total cost of ownership and the ROI for an integrated system? You have to look at the total solution. So that's the message I'm trying to give here today is look at where we're headed as a company, as a DOT, as a nation, in terms of all the fiber that's going to be utilized going forward, and how can we leverage it elsewhere? And then I'm not going to read through this in detail. I would consider this more of a reference slide to go back to after all the folks that follow me go into the depths that are required to show the detail here. But it is a proven technology in other vertical markets. It's perimeter and border security, pipeline monitoring, protection, and protection of underground utilities. So this is tried and true in many other cases. What's new and emerging, as Blaine points out, is the utility of using this on the roadside applications. And then what we hope to show you through the rest of this presentation and through the really exciting collaboration we've had for the last couple of years with Utah are the following things. And you can read them as well as I can say them, but we're looking at the ability to put in a complementary ultra low maintenance sensing capability that's always present there in parallel to many of the other sensors you already have on your roads. We're looking at a unique situation in that it's very low latency and it's going to provide consistency, speed, queue congestion, and travel times. It's also going to give you situational awareness, which we really dove into in this project, and you'll see that in a few minutes. It's not just the traffic monitoring, it's, my God, addressing accidents and all kinds of other events that can happen along your road in a way that no other technology truly can in a continuous manner. It's also, again, getting back to that robustness and sustainability and reliability. It provides asset protection for any right-of-ways in that third-party intrusion or anyone who either intentionally or unintentionally is trying to get into your system. It's going to be identified. And also, it's you can use it as an operational tool where you can monitor things that you planned on occurring in terms of listening for when they occur, when they start and they stop. And then finally, and this is very important going forward for our world, for that matter, it can reduce the carbon footprint by potentially reducing peripheral device density. So with that said, this is my final slide, and I'm going to pass it on. I hope I set the stage properly, and I hope I piqued your interest for the remainder of this presentation. So as we head down the road with visionaries like Blaine and UDOT, let's just ask ourselves what we could do right now to leverage all the new infrastructure that's going in with technologies that we never previously imagined. And then as a final takeaway and a request for people on this who are attending this presentation, either live or later on, we would love, as contracted ITS service companies, as affiliated companies or DOTs themselves, we would love to work with you to evaluate how to integrate this in your technology, look at the business model, and see how this could be another critical tool in your ITS toolbox. And with that, I thank you for allowing us to be present and participate in this presentation. And I'm going to stop my sharing and pass it on to Muriel again.
Perfect. Thank you so much, Paul. I think you have piqued our interest. We've had a couple dozen more people join us during your presentation. Let's go to Andrew. As Blaine mentioned at the top of the hour, Andrew and Alistair are joining us from Europe. So it's a little late in your time zone. Thanks for joining us. And let me just give a brief intro. So since 2010, Andrew Hall has been working on distributed fiber sensing technologies with a specialism in transportation applications in particular. During this time, he has progressed from installing and commissioning systems to becoming the global segment lead for transportation. He has been involved with the Technology Committee on the Fiber Optic Sensing Association, presenting webinars and helping with the production of technology primers for transportation applications. Andrew has a first-class Bachelor of Science degree from Bangor University in Wales. And with that, Andrew, feel free to take it away.
Thanks, Muriel. Okay, so I am going to give a technology overview. There'll be a little bit of an overlay from what Paul has said, but I want to focus on the journey from sensing through to valuable information that is output. I want to cover a few of the sort of common plots that the technology provides, before looking at some of the installation considerations for the fiber optic cable and how those have applied to some of the deployments within the canyons that we have done at Utah 2. Before then looking at the use cases. So I'll start with sharing some of the traffic monitoring applications before handing over to Michael. So how does the technology work? So ultimately, the essence of distributed acoustic sensing is the ability to convert a roadside fiber optic cable into a distributed sensor. This could be an existing single mode fiber optic cable. It could be a newly installed fiber optic cable, or it could be a cable that's installed overlaying into an existing duct, for example.
Andrew, I hate to interrupt.
Sure.
It looks like the black bar at the top of your screen. It's obstructing our ability to see. There you go. Thank you.
Sorry, no problem. Okay, so we have our asset, in this case, the road, and then we have the fiber optic cable that runs parallel to it. The technology needs a single core within the fiber optic cable. So if you have a multi-core, so 16 core, or a lot of different variations, it just needs one of the cores within there. When they manufacture the glass, there's a lot of scattering sites that are frozen out when they're pulling the glass through. So there's thousands of these every inch as they manufacture the cable. And this allows us to get a signal from it. And we do that by plugging an interrogator unit, an instrument onto the end of the fiber optic cable. And we shine a light pulse down that fiber optic cable. As that cable goes along, a small fraction of the light is scattered by all of these scattering sites, and that returns back to the instrument that is monitoring it as well. Because we know very accurately the time of flight of light through glass, we can equate the returning scatter that we see to positions along the fiber optic cable. So to give you an idea of sort of scale, like Paul mentioned it earlier, but for highway applications, we can monitor 28 miles in one direction, and we can monitor like 30 feet intervals of the returning scatter as well. That returning scatter that we see, or the returning light that we see from the interrogator unit, has its own pattern. But when there's an event that occurs in the vicinity of the fiber optic cable, such as vehicle movements, this might be a car that you don't see very often in the US, but more UK. But if you see vehicle movements, so trucks or passenger vehicles, they radiate acoustic noise, which actually vibrates and puts strain onto the fiber optic cable. This strain changes the backscatter signal that we see, and we receive that back at the interrogator unit. The technology is sensitive enough that you can see in people walking around the fiber and digging as well, and the strain from those events changes the backscatter as well. And this is why it's called distributed acoustic sensing, is that because we're sensing at the speed of light, we're able to send thousands of samples every second down the fiber. So we can monitor in real time over the whole distributed asset, and we're monitoring quickly enough that we can make sense of the acoustic signals that are occurring as well. All of that data is sent over to our processing unit, and the processing unit takes all of that information and it runs the classification algorithms through it. So it's looking for acoustic fingerprints of different events. So is it a car? Is it a person walking? Is the car moving, the direction of the car? Are there the buildup of traffic events such as queue and congestion? And then we send that out to, we have a user interface, which I'll show, but also as well, there's a suite of external interfaces that send it out to third parties. So this could be central command software. It also could be a SMS text message to individuals. And later on, I'll share the interface, the external interfaces that we had for this project too. As always, technology develops, and one of the developments is the increase of range. So now from an interrogator unit, we can actually monitor up to 56 miles. So 28 miles in one direction and 28 miles on the other. And to give you an idea of what the equipment looks like, so the equipment stack that you see here, this is one of the interrogator units that you see here, and the processing unit is a 1U rack server as well. So that equipment could give you an efficient route coverage of up to 56 miles. And it's a very simple and rapid installation. So once you connect to the fiber, you can receive sensor information within minutes, which can then start to be used to turn into valuable information as well. Because the equipment's located away from the road, there's no road or lane closures that are required. And because there's no power that's needed along the roadside too, it's an ultra low maintenance burden for monitoring that amount of distance. And it's impervious to weather, to road maintenance, wear, or renewals as well, and has a long life with a mean time between failure that's growing, but it's in excess of 10 years as well. So the valuable information that's output as alarms, is what a lot of people are interested in. So for operators, they don't want any interpretation. They just want that valuable information to say, this is an event, this is where it occurred, so that they can react quickly. However, because we're doing a multitude of different applications that we'll be sharing within this webinar, I want to orientate you with a couple of the common data plots that the technology provides as well. So these plots are used when we are looking at new applications to see what the signatures, the acoustic signatures look like, so that we can configure the classification algorithms to automatically generate alarms from them. And a common one is called a waterfall plot. So the waterfall plot is a real-time view across the whole of the monitored asset. So on the y-axis here, we've got time, and we're looking at 30 minutes. And on the x-axis, typically this is up to the, say, 28 miles that we are monitoring of the asset. But for this, it's 2 miles that we're showing here in this zoomed in area. And the color scale relates to the acoustic intensity. So we have low level white, through grays up to black, which is high level acoustic intensity. And the latest information, or the latest data, arrives at the top, and it gently pushes the information down the page, hence flowing like a waterfall as well. The waterfall is just an overview of the activity across the asset. So what it does is it sums specific frequency bands of acoustic energy to just give a sort of approximation of the energy. So it's typically set to 20 to 200 hertz, but it could be configured differently. Finally, there's a couple of different flavors, if you like, of the waterfall in terms of the color. So this is also a commonly used one, which is known as a jet waterfall, but this goes from blues through yellows, oranges, and reds to higher level activity. And there's a final one that I've got one slide on, where it's gray, which is low, and it goes through to white as well, which I'll share a little bit further on. But the technology is a lot more powerful than just the waterfall. So behind the waterfall as well, if we take a slice within time, but we could equally take a slice in distance as well. And what you see in the time slice is that there's a lot of other frequency bands that are available for us to use. So here we've got frequency that we're looking at now on this axis. And this is just to show you that although the waterfall is summing specific frequency energies, behind the waterfall, we can see a lot higher or a lot different frequency ranges as well. So for a typical installation that monitors 2 fibers, for example, we could monitor a kilohertz that we sample at. So we would monitor up to like 500 hertz that we could see as well, which provides a rich data set for our classification algorithms too. So finally, let's take the step to transforming some of these plots into valuable information. And I think it's always helpful to have like a video of an actual event as well that you can see to make sense of it. So on the top of this, to help orientate you with this video, we have a waterfall image again, but we're actually zoomed into a specific location. So this road here is about 20 miles long that we're monitoring, and we're zoomed into a 6-mile section of the specific road. And here we are looking at about 30 seconds of time and 6 miles there. And on the bottom, we're actually looking at part of the user interface that can be shown, and the colors relate to the speeds that are being generated from the vehicle movements as well. We have a number of times on the top, which are the travel times between the junctions as well. So the first thing that you can see is that there's a lot of lines that are on there, and these actually correspond to individual vehicles. So the thick lines, the thick black lines, are actually trucks, and the thinner grey lines are passenger vehicles too. And what we're going to focus on is the movement of the direction from left to right. There's also traffic moving on the other carriageway on the other side of the road in the other direction too. And I'm going to play this example of a specific traffic event and shows what that does to our outputs as well. So in this particular example, what we've actually got is a 2-lane by 2-lane road. And this particular truck here is carrying some plant material. It has a pilot vehicle, which is preventing any vehicles from passing in the passing lane. So you can start to see that the traffic is backing up. So as that traffic backs up, on our schematic, what we see is that the green starts to go into orange, and then eventually it will go into red. So we've got free flow traffic conditions in front, and we've got this traffic backing up as well. Now there comes a point where at this location, it's actually a curve in the road and the visibility is poor. But at this location here, the traffic starts to speed up a little bit. So the front vehicle is speeding up, the road straightens, the visibility is better. And at this point here, the pilot vehicle pulls in and allows the traffic to pass. So we've had a build up here. We've had the reduction of speeds. We've had reds that have popped up. A congestion alarm was generated. And now at this point where the truck starts to drop back into the traffic, into the general traffic, we return to normal conditions on the roadway. And then on our outputs, you would see this return through oranges to yellows and eventually greens, and the congestion alarm is dismissed. So the stream of information of all of the speeds and the alarms would be sent out to the external third-party interface as well. Okay, so now that you have an idea of some of the plots and the technology, let's have a look at some of the installation considerations. So as the fiber cable is the sensor, its importance is critical to that overall system as well. So I'm going to summarize some of the installation considerations, and then we'll drill down into a little bit more detail about what we found with the different canyon installations that were conducted at UDOT. As Paul mentioned, we're part of the Fiber Optic Sensing Association, and myself and Alistair and others on this call have helped with the technology primers and also the installation guidelines for highway monitoring as well. And you can find that on their website too. But there's 3 main silos for consideration. So number 1 is the cable construction itself. So the coupling between the glass core that we are sensing and the exterior of the cable, that obviously varies for a lot of different cables, and it can influence the sensitivity. So the good news is that the fiber is the technology, is incredibly sensitive, so that there is a lot of range in terms of what can be acceptable for the cable construction. But it also gives the possibility that you can install a cable that is actually optimized for fiber sensing, which gives some exciting possibilities for future installations too. The second silo is the cable installation. So the installation method and the depth also influence performance as well. So, you know, broadly speaking, the deeper that you go, the further away from the asset that you go, and the less signal that you receive. Finally, the cable position is important as well. So there's a number of factors which impact the acoustic coupling. One of the most obvious is the distance to the fiber. So if you're 5 miles away from the road, you're not going to pick up any signal. But when you're closer to the road and within the right of way, say that you'll be getting signal from the road itself. There's also attenuating structures. So if there are any noise cancelling walls or anything like that within urban areas, and the fiber optic cable is the other side of that structure, then you get a reduction of the transmission of the acoustic energy from the traffic on the road as well. There's also elevation changes. So if the fiber is located either far, far below or far, far above the fiber, then you will receive a reduction in the amount of signal that you receive. And then finally, road configuration. If you have an elevated section of concrete road and the fiber cable is buried below, then you won't get any signal for that section too. Because the technology works at sensing based on time, all of the different 30 feet sections that we have measurements for can be configured differently. So the sensitivities of our algorithm can be configured differently to take into account some of these effects. However, there are still some like particular sort of use case like the road configuration, where despite all of that flexibility, you won't get enough signal to be able to get good traffic monitoring information. So let's have a look to see what we found with some of the installations. So Blaine mentioned the installations that were the permanent installations that were done in the 2 Cottonwood Canyons, Big and Little. And there's also a temporary installation that was done on American Fork as well. So for Big Cottonwood Canyon, the general sort of installation comments were that within the canyon itself, concrete was used to backfill the conduit. Now, concrete, it's used in sort of soundproofing walls. It's not great in terms of trying to get a lot of signal. It attenuates the sound very well. It reflects a lot of it. So generally for this installation, this was the installation which was least sensitive, primarily because of that. There were a few exceptions. So in A that we see, which Blaine mentioned, there was a different fiber type, which was a 144 count micro cable single mode fiber. And this was gel filled, which gave a little bit better coupling. And this was the only location in this specific canyon that we got traffic in both directions that we could see. The next best area was at the end of the monitored canyon, where it was a different standard single mode cable that was there. And then finally, there was a different cable again, which was at the sort of, it straddled the micro cable in the region labeled as C, but this was with a single mode 288 count. So there was a few sort of factors in play, but generally for this one, the concrete that was used to backfill reduced the sort of sensitivity that we saw there, which had a knock-on effect, you know, for some of the sort of applications that could be used at that particular canyon. If we look at Little Cottonwood Canyon, so straight away you can see in this waterfall that there's traffic which we can see in both directions for most of it. So it was good for fiber sensing. And the main difference to Big Cottonwood Canyon was flowable fill was used for the backfill, and just sort of broadly it was more uniform too. So the fiber type was the same. There was fewer variations than Big Cottonwood Canyon, and the fiber as well was generally close to the edge of the road. It was off the edge of the road, but it was close and uniform too. There was a couple of exceptions where the signal was slightly reduced, but it's is easily configurable for our algorithms, such as an increase in the depth of the fiber cable at section A. And there was a couple of sections where the fiber was far from the road where we got some reduced signal, but you could still see some vehicle movements within there. And finally, the temporary deployment that was done within American Fork Canyon. So this was done where a fiber cable had been installed with fiber sensing in mind. So I think at that time, UDOT knew that this project was happening, and this cable was installed with our technology in mind. So the big difference was that the fiber optic cable, so firstly, it was uniform again, so it used the same cable, but also what they did was, although it was off the active lanes and it's a narrow canyon road, but it was still like within the road itself. So the conduit was buried at similar sort of depths, 2.5 feet to the other canyons. It had a similar backfill that was used to Little Cottonwood Canyon, but because it was within the roads itself, the signal was vastly sort of improved, certainly from Big Cottonwood Canyon. So in terms of variations across the canyon, it really was minimal. And the main difference was the creek noise in the lower part of the canyon. In the standard frequency bands that were used to produce the waterfall, you can see a lot of noise from the creek canyon. But because we can use frequency bands different from what we sum up here, you can see higher frequency bands where the vehicles are clearly visible, and this is reduced as well, or whitened. So to summarize the installation comparison, American Fork was excellent for fiber sensing, primarily born from the fact that it was very uniform. It was within the road itself. Little Cottonwood Canyon was very good for fiber sensing. So again, you could see traffic in both directions. And there it was relatively close to the road, but off the road. And there was little variations along it. And then finally, Big Cottonwood Canyon, as we see here, we only see traffic movements in some specific locations along the canyon. And this was borne out in the area where we had the micro duct, but it was ultimately reduced the sensitivity because of the concrete that was over the fiber as well, which effectively attenuated a lot of signal coming from the roads, from the Big Cottonwood Canyon Road. Okay, so let's have a look at some of the applications of the technology. During the project, we touched on, but there was some analysis of the existing functionality of the traffic monitoring applications. There was some applications where algorithms were developed during the time of the project, which such as avalanches. And then finally, there was also other areas that we opportunistically found information into. And I'm going to present on just the traffic monitoring applications and an overview before handing over to Michael. And Alistair will give more detail about a lot of the other applications too. So as discussed, there's a number of functionality that can be given. So we can output the speed for each travel direction for any given road for every 30 feet along the monitored section, and output that every second. So for example, if we had like a 2-lane by 2-lane road or a 3-lane by 3-lane road, we would output a speed for each of those driving directions, an average speed across the lanes every 30 feet. And then we use the speed information as well as some other parameters to look for a convoy of slow moving vehicles and to trigger for congestion alarms. We can also look for the buildup of queues, and I've got an example to show you what that looks like, and trigger automated alarms. And with the rich speed output that we have, travel times can be configured for any given segment of interest. So this could be between intersections, it could be between well-known sort of tourist routes from, say, the start of the canyon up to the end too. And also where the fiber crosses the road. So any sort of off or on ramp on an interstate, but for the canyon roads, for any junction, if the fiber is on that side of the road, then we can actually estimate a count and volumes at that location too. And we can update that, every second for all of that functionality. So there's real low latency in terms of the generation of alarms. So looking at traffic monitoring and how that sensor data is then converted into speeds. So if we look at like a waterfall plot of Little Cottonwood Canyon, so we're zoomed into a section here, and we are looking at about 3 hours roughly on the y-axis. If we split that up so that we can split those up into driving direction, what we can do is we can overlay our speeds onto this plot. So in this plot, gray is low level and white is high level, acoustic intensity. So what we're expecting is that these white lines that you see are the vehicle trajectories moving in up the canyon and down the canyon. So when we show what the output of the speed output is, these are then overlain onto the plots too. So green shows that it's going at a sort of free-flowing speeds within the canyon. In some areas of the canyon, it's a lot lower than this, but just to give you an idea. And then we can also see areas where we have got vehicles which are moving a lot more slowly. So on the up canyon at the bottom, there's a vehicle here which is very large, presumably, or it's going very slow, and it's slowing, and then it's moving very slow in this area before sort of speeding up. It's a pretty tortuous road, so it could be a lot of bends in the road and things that have to be navigated. And then finally, if we look at those instantaneous speeds and then how we sort of use that for data outputs. So for the American Fork Canyon, what this video is just showing is our user interface, but we have our waterfall display that we see in the top right. We then have our instantaneous speeds, which are being output. So you can see that they chart the individual vehicle trajectories very nicely. I'm only showing the up canyon direction, so you can also see that there could be toggled the traffic that's moving on down the canyon as well, and we could show that. But those instantaneous speeds are then averaged into speed outputs that are then presented on the bottom schematic, shown on our map, but these could be pumped out onto other parties, other interfaces as well, and ingested into other software. So these are like what the speed outputs look like. And to give you an example of an event that occurred, an actual traffic event. So earlier this year on the 3rd of February within the Little Cottonwood Canyon, there was a queue that was evident there. So this plot that you see here is for 24 hours of speed outputs. So the left-hand side here is down canyon and the right side is up canyon. And there's some black areas here, which is just where nighttime conditions and that you get lower flow. And then in the daytime, we get it sort of ramped up there as well. And what draws the eye is this highlighted area here. So it looks almost triangular here too. And this is actually the queue that built up. So when we sort of zoom in and look at, say, 4 hours in time and 6 miles, then we can see a little bit more granularity. So you can start to see in the free flow conditions, the individual vehicle traces as such. But here there's a very sort of distinctive pattern that we have of slow speeds with no sort of data in the middle. It's like stationary traffic. And we've got like a backward propagating wave of a queue that's building up in this direction. So the traffic is flowing freely in this direction from right to left before 3 o'clock. And then at 3:22, we see that the queue starts to build at that position and stretch back up the canyon for 2 miles from marker post 6.7. For the next few hours, so just under 3 hours, the queue sort of remains and the back of the queue varies in place and oscillates at a time. We have some vehicle movements that are moving through and coming out. but it eventually clears at 1808 as well. And then finally, we have free flow traffic down the canyon. And finally, just to finish off before I hand over to Michael, just talking about the integrations for this particular project. So the two permanent installations within Big Cottonwood Canyon and Little Cottonwood Canyon that we have, they fed in traffic monitoring information into the Blinksy Pulse dashboard. So this was done with an interface so that it was available over the cloud and used as part of the tools that are used by UDOT to be able to see and visualize, record and analyze different real-time events. So this was just the alarms that were coming out for congestion and queue detection, travel times for specific areas of interest within the canyon, and the speeds were output for every 30 feet along the monitored sections too. As I mentioned, so there was some applications which are emerging where data was looked at and classification algorithms were implemented to output alarms for specific events. And for avalanche events that Alistair will cover, we interfaced with the relevant UDOT stakeholders by sending emails when avalanches occurred, detailing the position, time, etc. And then finally, for this technology, it has data recorders on there. So some of the plots that you've seen and also just the raw data is recorded in a rolling recorder, which for the raw data is roughly about 1 week, but could be extended to more. And for the waterfall data is a lot more. But this is done so that it allows us to extract data from any events that occurred. So there was a lot of other applications that it was looked at, the technology was looked at, but there was also opportunistic events, which Alistair will cover, of really interesting events that we were able to look back into the data and then provide a sort of forecast on the applicability of a classification alarm to, and in some cases, configured and set those up so that it could generate alarms to the relevant stakeholders. Thanks a lot for listening, and I'll hand it back over to you, Muriel.
That's great. Thank you so much, Andrew. We'll now turn to Michael Sheffield. Michael has been working on pretty much all of these deployments over the years, and is quite the subject matter expert and resource for UDOT on their deployments. So I'm pleased to introduce Michael Sheffield. He is a transportation engineering consultant who specializes in the connected and automated vehicle industry. He is passionate about leveraging emerging technologies to improve and enhance safety and mobility in Utah. He's involved with Utah's V2X planning, deployment, and evaluation. When Michael is not evaluating the impact of connected vehicles, he can be found with his family working on the ranch or playing pickleball, which is very popular here in Utah. So if you've never been, come visit our state and play a little bit of pickleball. I'm sure Michael can set you up. With that, go ahead, Michael.
Thank you. And you're quite right. Pickleball has kind of taken off and gained in popularity over the years. Grateful to be participating in this webinar. This is a very neat and exciting deployment, using fiber for situational awareness along roadways. As a reminder, with the ATCM-TV grant, Advanced Transportation Congestion Management Technology Deployment, the D is deployment. And what we did here was deploy a fiber optic roadway monitoring system with the goal, as has been alluded to, increase our real-time situational awareness. Our objective with this is to leverage existing fiber optic cable for real-time roadway monitoring. We've talked about some of the canyon conditions, and some of these things have been said already, but these canyons are major recreational areas. It's winding, mountainous terrain, And there are significant transportation challenges here. There's congestion, limited parking in the canyon, limited transit, and there are major detection gaps along segments of the roadway. There are many different kinds of data that UDOT uses to monitor their roadway networks. Probe data is an example that is almost throughout any roadway. It's a purchase data set. So I did just put one icon at the beginning of each of these canyons, but recognizing that the probe data extends throughout these canyons. Whereas some of the point detection that is deployed is specific to that part in the roadway. Similar to point detectors, there are also Bluetooth sensors. And for these canyons, you can see the locations of many of these devices. For the existing traffic monitoring systems, each of these has their own strengths and benefits and limitations, and I won't go into all of them right now. But many of them are purchased. Some of them only are able to detect a small portion of the roadway. Some of them are periodic. Data is only collected every minute or every several minutes. So using multiple data sets, merging them together provides an enhanced understanding of what is actually happening out there on our transportation system. And this is one of the things that this fiber sensing system adds considerably to the existing devices and traffic monitoring systems. For the fiber sensing, the ability to detect road users is a critical part of this. We're still working on automating the total count of roadway users that are detected. And that's partially because, as was alluded to earlier, the strength of the signal that a vehicle makes is dependent on many factors. And at different parts on the roadway, the fiber cable might be a different distance, a different depth, even encased in a different material, all of which affect its ability to detect road users. But we went through and for a portion of this did a manual classification. We did a temporary recording of a couple of UDOT's cameras, and I'll demonstrate by showing this part of the waterfall diagram with distance and time. And these vehicles that I've indicated with the red arrows, these detections are vehicles. They have a deeper, brighter red, indicating that the vibration is stronger, and they're traveling about 45 miles an hour along this canyon road. You can also see some lighter angled lines kind of behind them. These are cyclists. I've highlighted two of those blue arrows that correspond to the above pictures, indicating that, in both these two instances, we have 3 cyclists and 1 cyclist, and you can see the distinct trace or trail or the ability of the system to track and monitor them as they travel down the roadway. There was also an exciting instance of some runners that were detected, and they must be running right on top of the fiber. You can imagine that people running wouldn't make that much of a vibration compared to cars, or but here we can see the detection of these runners traveling at about 6 miles an hour. Now, the classification, like I just mentioned, is more challenging, and will likely be augmented by other traffic monitoring data. Like radar, for instance, can detect the size or width or length of the vehicle, whereas this system that's one of the things that it isn't able to do as well as other technologies. But overall, the fiber sensing effectiveness under ideal conditions, which I specify because we've demonstrated that there is a large range of the capabilities of this system, dependent almost entirely on how it's installed, where it is on the roadway. But in locations where we have the fiber installed under these ideal conditions, we have continuous roadway detection. There aren't gaps in the roadway like you see with point detectors, but we're able to continuously detect vehicles as they travel the length of the roadway. It is also very comparable to the traditional aggregated traffic monitoring systems that are currently in use. And I say aggregated because a lot of these probe data sets and others, group data points together and to provide an average. But this system tracks, every vehicle, and the speed is within 5 miles per hour of these traditional systems that are aggregated. The travel time is within 1 minute, recognizing that those other detection systems have a window where they detect, whereas this is, as Paul was describing earlier, several feet at a time granularity. And the ability to count vehicles, more than 99% of the vehicles are detected, with limitations that exist for other technologies. If vehicles are traveling too close together, it's difficult for any system to differentiate those two vehicles as separate. Similarly, if speeds are very slow, slow moving vehicle would create less vibration in the roadway. So this system, as well as traditional traffic monitoring systems, they both struggle with lower speeds. With the caveat that we are able to, with this distributed acoustic sensing system, see and detect vehicles, cyclists, and runners under these ideal conditions, and being able to have that understanding of all users on the roadway has an enormous safety potential that we haven't even tapped into yet. In addition to these road users, there's the detection of other events affecting the roadway, which Alistair after me will cover more: crashes, avalanches, landslides, as well as the unique use case that we discovered of being able to produce turning movement counts at simpler intersections. So with that, thank you, and now we'll turn the time back over to you, Muriel.
Fantastic. Thank you, Michael. So now we will go to Alistair. Alistair Murray obtained a master's degree in physics from the University of Exeter in 2010. before completing a PhD with the Electromagnetic and Acoustic Materials Group in 2014. He went on to join Connects to work in the Acoustic Stealth Materials Group. In 2018, Alastair moved to OptiSense, which is now part of Luna Innovations, where he currently is the technical authority and provides guidance across the business about what can be done with DAS. Key areas that Alastair is involved in include rail, traffic, and infrastructure monitoring, as well as pipeline leak detection. Alastair?
Thank you, Muriel. Let me just share the right screen. Pleasure to be here with everyone. Yes, it is getting quite late here in the UK, but it's a wet and windy evening, so this is a much better way to spend my time. Okay, so this section is really talking about some of the incidents and events that we saw in the canyon other than traffic monitoring. And I want to go into a bit more detail about the analysis that we can undertake. But I would like to stress that ultimately, the purpose of the system is about delivering simple alerts and situational awareness to the user rather than asking operators to undertake the type of analysis or investigation that I'm about to show. Okay, so this is a map showing the 3 different routes that were covered and a selection of the events that were detected in the canyon. This isn't an exhaustive list, but it's some of the more interesting events that I feel we saw, and importantly, there's some ground truth behind each of these that allows us to actually verify what happened. I won't talk through all of them because I'm going to talk through all of them in a second, and I'm aware of the time. So let me start following on from Michael's talk with looking at turning movement counting. As Michael said, turning movement counting is an application area that came up during the trial deployment in American Fork Canyon. And here the idea is to identify how many vehicles are pursuing different routes and intersection. In the image that I show on the screen, we can see Route 92, the American Fork Canyon Road, running left to right, highlighted in red, and the road up to the Tibble Fork Reservoir, highlighted in yellow. And the fiber itself is the light white line and runs east along Route 92 and then follows the Tibble Fork Road. Now, different vehicles can take different routes via these 3 roads, which I'll get to on the next slide. And importantly, for this particular analysis, there's a camera at the fork that gave us access to ground truth information to do a comparison. So vehicles traveling along the road, heading east on Route 92 up to the Tibble Fork Reservoir. If we look at the waterfall image on the right-hand side, they will create a line that moves from left to right in time and covers the entire route. Vehicles that are traveling east on Route 92 and head past the Tibble Fork junction will start with the same line, but then appear to just disappear into the ether. Vehicles heading west on Route 92, we won't pick up until they turn up the Tibble Fork Road, and so they'll appear out of nowhere, heading left to right. Vehicles heading west on Route 92 and going straight past the Tibble Fork Reservoir will also appear out of nowhere, heading right to left. Vehicles coming down from the Tibble Fork Reservoir, then heading west on Route 92 will cover the full display, heading right to left. And those coming down from the Tibble Fork Reservoir and then heading east on Route 92 will disappear. So we've got 6 very clear distinctions between vehicles performing different maneuvers. And taking a 1-hour section of data, we performed a manual check against the camera information that we had. So for the purposes of counting the vehicles detected by DAS, a visual assessment was undertaken with a judgment made as to whether a distinct vehicle track could be identified. And looking at each of the potential routes, the counts over the 1-hour period are broadly similar. The most notable discrepancy is where the angle of the camera made it impossible to identify vehicles going west on 92 up the Tibble Fork Road. And a couple of other minor discrepancies. The fiber was judged to have been unlikely to be able to separate out two vehicles traveling in tandem and to identify 2 motorbikes. As mentioned, this would be a novel capability, but it should be noted that this type of analysis doesn't necessarily need to be undertaken in real time, And so it allows us to apply much greater processing than is required for on-the-edge capability. And moving on to something, one of the original ideas for installing this system in the Big and Little Cottonwood Canyons is the detection of avalanches. And the system was installed in late 2021, and we were told that Little Cottonwood Canyon is a renowned hotspot for avalanches. And so we waited patiently throughout 2022 for this to come true. Needless to say, we were waiting a long time. Then in 2023, it seems that everything went a bit crazy in the canyon. And in April, the canyon actually ended up closed for nearly a fortnight. And I gather that more snow has been seen this year than has been seen since 1982. A quote from a UDOT spokesperson suggests that over a period of 5 days, more than 30 slides covered the 2-lane road. Moving on, this is a map image showing a section of the Little Cottonwood Canyon route, and you can see highlighted by pink and red shapes some of the avalanche chutes that occur along this route. I've highlighted 4 of them in red, which are some events that I'm going to share with you. This first route, this first avalanche at the coal pit, just to reiterate what the display shows, we have distance along the horizontal axis and time up the vertical axis, and then the color scale is indicating the detected signal energy within the frequency band that we happen to be looking at, with blue representing low energy and red representing higher energy. What's clear about this signal is that there's a big red splodge that's appeared in the middle of it that is much louder than anything going on around it. What we can take away from this is that we can measure the width of the signal, affecting around 700 meters of fiber, and the signal lasted about 30 seconds. Moving on to the second event, this is at the Lisa Falls chute, where there were actually 2 avalanches experienced in quick succession. The first produced a signal that affected around 800 meters of fiber, lasting around 30 seconds, while the second event impacted around 1,000 meters of the fiber and lasted much longer at 60 seconds. To the bottom right of this image, you can see another very large signal, which is being generated by one of the snowplows along the route. Now, the eagle-eyed of you might spot a vehicle narrowly being missed by the first avalanche. Don't worry, we're going to return to this this particular incident to take a look at it in a few slides' time. Now, quickly moving through the Tanners avalanche, which generated a signal around 900 meters and lasting for about 30 seconds, and an event at White Pine, which also generated an event covering around 800 meters of fiber and lasting about 30 seconds. The important thing is that for us is that we were able to identify all of these avalanches, and that all of them created very similar signals. And in terms of configuring a system to detect something, it's a lot easier when everything looks the same, rather than producing a different signal every time. Now, you might be asking yourself, wasn't this project supposed to be about situational awareness rather than producing pretty wall art? And you'd be correct. So while we had some ideas when we started the project about what an avalanche would look like on the system, and various detectors were implemented, these were largely assessed for nuisance alarm rates through 2022 and found to be deficient. But after being able to gain valuable information from this fortnight of avalanches that were experienced, we were able to refine the detection algorithms and produce something much more helpful. So returning to the Lisa Falls avalanche, here we have a grayscale waterfall highlighting some of the alerts being generated by the system as the data that we acquired from the Lisa Falls avalanche was replayed through it. So several vehicle alerts are identified. This detector was primarily aimed at larger vehicles, which is why some of the smaller signals are smaller vehicles that are quite clear on the waterfall aren't being detected. And then the 2 avalanches themselves are also highlighted with the red avalanche symbol that we've created. And in both instances, an avalanche warning is produced well within the well within 30 seconds of the start of the event. Now, the information in these alerts can provide rapid warning that an avalanche has occurred, along with the location of an event, allowing for a swift reaction. And you can imagine that unless there happens to be a vehicle in the area at the time or camera footage showing, then the fact that these avalanches has happened may go unnoticed for a lengthy period of time. Looking at this historic information that's available, we're also able to consider whether there were any vehicles in the vicinity of the avalanche at the time. For instance, the vehicle that was narrowly missed by the first avalanche, but perhaps more importantly, whether that vehicle got out of the vicinity of the avalanche. As has been alluded to by Andy and the other speakers, the waterfall itself is one snapshot of what we can see with DAS. So if we take a look behind the signal by taking a spectral analysis of one of the channels through each of these avalanches, we can see the spectral content that is being generated in the optical signal as the avalanche occurs. Now we can see considerable low frequency signal between 5 and 35 hertz for about 30 seconds occurring in the data. And similarly for the second bigger avalanche, we get a much higher, a greater energy content up to higher frequencies. Moving on to something slightly different. This was a truck crash that happened at the corner of the Tanner's avalanche area. And in the background of this image, you can make out a truck that has tipped over onto its side. I don't know what caused the accident, but we certainly saw what happened. So taking a look at the historic data for this image, again, distance along the horizontal axis and time up vertical. There's a few fairly faint vehicles that can be identified moving right to left on this particular image, but the clearest signal is that of the truck coming through, and then a very large impact being generated. And you may also notice this vertical signal lasting for several minutes, for around a minute after the impulse. So once again, if we take a look at the spectral content behind the signal, we can see at the time of the event, there is a massive impulse that generates a huge amount of energy across a very wide range of frequencies. And then after that, after the initial impulse, which is presumably where the truck has flipped over onto its side, we can see this vertical line representing a tonal content at around 32 hertz. Now, this is likely to be the turnover frequency of the engine. At 32 hertz, that's roughly 2000 RPM. So there's a lot of information that we can pull out from the signal that perhaps isn't particularly interesting, but can potentially be useful for various different scenarios. Moving on to a similar event, this was another truck crash that this time happened in Big Cottonwood Canyon. And unfortunately, this incident actually led to several injured parties and a fatality. So whilst we didn't have any detectors set up to actually detect this event, we can look back and tell the story of what happened, which is potentially useful for the post-analysis where sometimes facts on the ground may not be known. So on this slide, I'm showing on the left-hand side a map image with some key locations highlighted. In the center, we have a waterfall history of the event. Now at 9:22 in the morning, the truck is traveling down Big Cottonwood Canyon and comes through the switchback at location 1. And at this point, it's traveling about 22 miles an hour. And then we can see as it enters into this downhill section, marked by section 2, that it accelerates up to around 60 miles an hour. The speed limit on this road is, I think, 50 miles an hour, if not less. Typical speeds are certainly less than 50 miles an hour. Then at 9:23, there's a large impact observed right at the end of this more highly coupled section. Now, the impact itself doesn't look particularly impressive on this waterfall, and that comes down to, again, this fact that this is a snapshot of the data, and in order to see these vehicles, we have to look at lower frequencies. If we were to take a spectral content through that impact itself, we can see prior to the truck coming by, there's very little energy, even down to the very low frequencies. But as soon as that crash happens, there is a massive impulse. Now, in this particular case, an alert could certainly have been produced on that event, and it certainly wouldn't have prevented the event. But what we could also have done in this particular scenario is produced an alert indicating that a vehicle is traveling at an unsafe speed. So whilst this wouldn't have prevented the incident from happening, it could potentially allow a faster response to a scenario where every second counts. I don't know how this event was reported, but it's easy to believe that the call itself was made by one of the vehicles following behind the truck. What if they hadn't been there? What if this was an isolated section of road and there's no one else around? A smaller incident that happened in Little Cottonwood Canyon, one of the vehicles traveling down the road actually slid off the road during the, presumably on some ice. The image on the right shows a truck with I doubt that you'll be able to make it out, but there is actually a cable coming out front of the truck off to the left-hand side of the image, where it's presumably attached to this vehicle waiting to pull it up. This vehicle would have been traveling downhill on the right-hand side of the image, so the far side relative to what you can see. So what did we see on the system? Taking an overview of about 10 minutes around the event, we can see many vehicles heading from right to left down the canyon, and a few fainter vehicles heading from left to right up the canyon. Within the white square that I've highlighted, there's a clear change in the vehicle behavior, where we start seeing some vehicles coming to a stop, and a propagation of these, the stopping points moving backwards along the canyon. And then later on, these vehicles start up again. Let's take a look at this in a little more detail by zooming in on where the event itself occurred. So again, we can see several vehicles moving right to left a bit more clearly now. And this first vehicle, if you follow my mouse, comes along, and then there is an impact, which I'm going to highlight in a section in a second because it's not particularly clear here, which then slows down, the gradient of the line changes, and the signal disappears. The vehicle behind it does a similar thing, and then as that impact happens, that vehicle, who presumably could see it, slows down and carries on. So let's first take a look at the impact itself. If we change the timescale and the colors a little, this becomes a little more clearer relative to everything else going on around it, and there's the potential for this to be detected. Now, what follows is a little bit of a speculative story because I don't know what happened in this scenario. I've highlighted the two vehicle routes that I've previously talked about. What I didn't mention is that after this vehicle slows down and disappears, it appears that that vehicle actually continues on very shortly later, suggesting that this isn't the vehicle that slid off the road. Now, being able to dive into this data in a little more detail, I believe that there is actually a third vehicle that started around this point and travels very closely with this second vehicle, and this one doesn't make it out the other side of the crash. As I say, I'm speculating, but it is quite interesting, I think, to be able to go back and analyze these events and potentially see what might have happened when you don't know what happened. So moving on to something else completely different, a serious weather event. Back in August last year, there was a vast amount of rain that fell in over Utah, which led to flooding in the canyon. So here in the photos, we can see a mixture of rocks and water that were covering the road. We don't specifically have any detectors set up looking for these things, but what we can see in the waterfall is really quite interesting and is certainly highly detectable. So the event on the left-hand side this actually originates at the location of a culvert running underneath the road, just to the east of the Little Cottonwood Canyon boulder. And what I speculate is happening is that given the sheer amount of rain coming down during this period, my suspicion is that this culvert started overflowing and the water is now flowing down the road, which we can see moving along at around 2 miles an hour, generating a very large signal. The event on the right is also the result of flooding. We're detecting the signal being generated by that flow of rocks and water moving down the canyon. It's a bit more subtle than the event on the left, but also highly detectable. The near horizontal stripes that you can see in the background of the waterfall, these are vehicles moving along the road. But again, as I've alluded to in some of the previous events, you can imagine that during much quieter periods or on quieter routes, it could potentially be a long time before anyone is notified about a potentially dangerous scenario that's arising. In a similar type of event, and extreme weather, we have a mudslide that occurred earlier this year. So here's a couple of photos taken from UDOT sources showing the effects of the mudslide covering both lanes of the Little Cottonwood Canyon Road. And these were taken later on in the afternoon around 4 p.m. For the left-hand image and 4:50 for the right-hand image. A quote from a newspaper report suggests that the start of this mudslide actually occurred around 2:30. So let's take a look at what we saw on the system. So here again, we have a waterfall image, first of all looking at around 4:50, and we can see this red splodge of data, which is affecting quite a large section of fiber and lasts for a couple of minutes. There is a slight time discrepancy between the video and the waterfall data, but I believe that that's a time discrepancy rather than an error in what I'm highlighting. Now, if we look earlier on in the day, this is where there's no video footage available that I'm aware of. You can actually see 5 earlier mudslides occurring at the same location between around 4:25 and 3 o'clock. And so that story about it reportedly occurring around 2:30, I don't know how it was originally notified, but it could well be down to this vehicle that came along and would very much have seen the effects of that mudslide. Okay, so before I finish off, and I think it's appropriate that I'm about to end with this, I want to share a story that occurred a fortnight ago about a utility cut on the fiber. A rather mean-looking machine shown in the photo accidentally cut straight through a power cable and the comms fiber running up to the Little Cottonwood Canyon Resort. Cut itself was reported by the system within seconds of the alert being generated. And in this instance, it actually sent a notification to OptiSense rather than to UDOT because we were still in the process of configuring those email alerts. And I passed that information straight on to our colleagues. And the inspection later that day revealed that the fiber and power cable had been severed by works taking place in the area. Thankfully, they were able to repair it by the next day. Let's take a look at what we saw on the system. So here's a waterfall overview. The clearest point is the fiber break that occurs in the top right, where we suddenly have a loss of signal. You'll also notice these horizontal stripes running off to the side. These are indicative of massive disturbances which are causing polarization changes in the fiber. And because we get a polarization change, this affects every part of the fiber beyond that location. This signal leaping out to the left-hand side is likely to be being caused by the power cable itself being severed. So it's great that the system alerted on the event, but that's after the fact. And it certainly potentially helped allow a rapid response. But the question is, what could what could have been done beforehand. So if we take a look at a longer period of time, for about 20 minutes prior to this event, there is a considerable degree of signal being generated. And if we look at the spectral content, we can see quite a large amount of energy growing over 20 minutes and getting stronger and stronger and into higher and higher frequencies. So while we didn't have anything specifically set up to detect this, you can see that one of the detectors we did have set up went off several times throughout this event prior to that. Now, 20 minutes is much more likely to be enough time to make some calls and check whether there is any engineering work going on and check that the crew is aware of utilities in the area. So I apologize that we are at 10 to 8. So let me very quickly summarize. As has been stated before, DAS is a proven technology in other sectors and has seen great success, particularly with the protection of assets from third-party intrusion. By using optical fiber as a passive sensor, it allows us to discreetly cover many, many miles without any power requirements along the fiber and has the potential to reduce the need for peripheral device density. And we can monitor a multitude of parameters with DAS, such as traffic conditions and event detection. But one of the important points I wanted to make here is that once the system is installed, the capability can be improved and added to via software developments rather than through the installation of new or additional hardware and sensors. And with that, I will hand back to you, Muriel. So thank you all for listening.
That sounds great, Alistair. Thank you so much. Well, thank you all for continuing to stick with us. We have one more presenter, and if we have time after Chuck's presentation, we will open it up for Q&A. I would note that many of our presenters have been responding to your questions as we go. If we don't get to your question, we will follow up with you. So with that, I'm going to introduce Chuck. Chuck Valise is a project manager over software development projects in GIS at the Utah Department of Transportation's technology group. He has been instrumental in UDOT's connected vehicle technology projects, specifically with software oversight and standardized message development. He is also engaged with connected vehicle standards development. Chuck has more than 35 years of experience working in the software industry in both the public and private sectors. He has worked in civil engineering, aerial photography, and mapping. With that, Chuck, feel free to take it away.
Thank you, Muriel. And I will try and be very quick here because I know there's not a lot of time. And there we go. So I just wanted to kind of wrap up what the other speakers have spoken about. And we got a great explanation from Alistair and Michael and Paul's overview as what he does in more of an administrator and a strategist regarding the fiber. So what we found out is fiber placement, the type of fiber and backfill are actually critical to doing your installation if you want to use this technology. So as UDOT moves forward, if we determine that this technology is something we really like and we want to continue to use, as future fiber is being installed, we need to be fully aware of how it's being installed. And if we're going to be using OptiSense technology on that fiber, then we have to follow the recommendations of the end installation so we can get the best data we can. The team spent considerable time tuning the algorithms. This whole system of detecting events is really a pattern recognition system. As events are detected in the fiber, different types of events generate different patterns. And that is what Alistair and Andrew and the team at OptiSense have been doing, is building up a library of these various event types based on the patterns that they see coming back. And as you can tell, they vary quite a bit between crashes, incidents, avalanches. Alistair mentioned that we've been waiting for 2 years to get some snow in Localwood Canyon. Well, this past winter, there was 903 inches at the top of the canyon at Delta Ski Resort. That's 75 feet of snow. That's a huge amount. I also have a background in snowpack management and snow hydrology. And the amount of water that's sitting up there is just incredible. So when these avalanches occur, they're huge events. They're so powerful. The picture that Alistair showed of the first picture he showed of the avalanche, where actually you could see the track of the avalanche where it crossed the road and where it took the trees out. I drove the canyon this summer looking at that specific site. And the conifer trees, the evergreens that were there, were very large spruce trees. They were snapped off like they were toothpicks, wooden toothpicks. It was amazing the power. There was 25 feet of snow that was on that road when the avalanche occurred. So being able to detect these events is, as soon as they happen, is what we need. And as Alistair mentioned, that we are detecting these events before anyone can observe them. And if you're driving in a canyon late at night and an avalanche occurs at 2 or 3 in the morning where no one is around, if there's not a lot of light in that canyon, you can turn the road and all of a sudden be smack dab and, you know, looking at a 25-foot ball of snow that you could hit. So detecting these things as soon as we can helps us immensely. And building up this library is exactly what we need. Now, data analysis of this type is not trivial. Based on the information that was presented, the waterfall charts, understanding raw information, it takes a lot of skill. In fact, again, here's just reviewing a slide that Blaine had showed. You know, looking at this thing, when I first saw the waterfall, I thought, what the heck is this thing? It takes experience. But the whole idea is once we can get this system calibrated, we don't need someone to look at this data. We want alerts generated. The data is there for someone who really wants to get at it. But the goal is when crashes, when avalanches happen, landslides, flooding, whatever the event might be, that we can detect these things and immediately send alerts out. That's where the system is so powerful for us. Now, integrating DAS into daily operations, you know, how do we do this? Policy needs to be created for what do we do with these generated alerts? I saw a question that someone had put in there is what is the lag time between an event being detected and when an alert is being sent or received by our traffic operations center? Well, this past winter, we were still calibrating the system, waiting for these events to happen. And when we also experimented with alerts. So alerts at the end of the season were sent to the head of the traffic operations center, the operators themselves. And so we just experimented with getting these alerts working. So this next year, we're going to set the policy, working with the operations group to determine, okay, who's going to get the alerts? What happens when they get the alerts? What are they going to do? So that aspect is still being determined as we speak. The next thing is the DAS alerts that are generated. They need to be verified during early stage of deployment. Again, that's the calibration of the system. Is when something comes down, how do we know it's a landslide or an avalanche? How do we know it's just a crash? So building up that pattern library so that the system can know what it is and sending it to us, we can then feel good about the system. So over time, with operational experience with this DAS system, and knowing that when events occur, we can verify it through cameras or whatnot. You know, Alistair showed pictures of the mud on the road, that we can say, great, here we have, you know, photographic evidence and video of when it occurred. We can correlate that with the DAS system, and we feel pretty good about this is how this type of data coming through, what this event really was. So over time, UDOT will be able to trust the data and the alerts generated by this system. And I hope everyone has enjoyed this webinar. This technology is really amazing what it can do. And it's been around, but it hasn't been around much for transportation or avalanche detection. So we have been very, very happy working with OptiSense and seeing what this system can do for us. So it's intriguing and we think it will be useful. That's it for me, Muriel.
Perfect. Thanks, Chuck. I think you set a record.
Okay.
Thanks for keeping us on track. So we have 1 minute remaining. Unfortunately, we are not able to get to kind of Q&A with you all right now, but we will follow up with you. We do just want to note that we have one final webinar in our series. It's scheduled for Wednesday, October 4th from 11 a.m. to 1 p.m. Mountain Time. We hope you can attend that one. It'll be about automated vehicles in Utah and what we've done there with that deployment. So definitely worth watching and participating in. With that, thank you so much for joining us today, and we'll be in touch with all of the webinar materials and the recording within a week. Take care.